Okay, so let us start with electrostatic energy. Let's ask the question, how much energy is stored in a charge configuration or in a field? And how do we do that? We do that by looking at the work done in assembling any charge distribution. So in the first step in that case is to ask the question of how much work is done in bringing a charge Q in a field E, let's say. Okay, this we have already done in your earlier course also. So let me write down, it is work done is minus infinity with a reference. We'll bring it to some position R. The force is F. Then it's line integral F dot dl. That's the work done. In our case, Q is coming in a field of E, and hence we can quickly write it down as R Q E dot dl. Now that E dot dl reminds of potential, but you can also write down this eliminate E by in favor of gradient of V, and in that case it has become a plus. I've taken the minus out, infinity to R grad of V, Q grad of V dot dl. All right, and I assume that the V of infinity is equal to 0, and in that case, by gradient theorem, this is nothing but Q I've taken out, Q V of R. I could have actually obtained it directly from here to here as well. Okay, so what is important is we have the work done is, first thing, it doesn't matter how you brought it because it's a conservative force, and the work done is wherever you place it, the potential there due to the field into Q is the work done. So this we already know. So having done that, let's ask the question, how much energy do I spend in assembling a charge configuration, or how much work I do, okay, in assembling a charge configuration. Let's say this Q1, Q2 and Qn are sitting in infinity, and I want to now put it in some configuration in here. And so I'll extend it to n discrete charges with Qi, I going from 1 to n. But let's start with 1, 2, and 3, and then we'll, so let me bring Q1 to my area where I want to put it. Suppose this is the appointed place, and I nail it down at here, Q1. How much work did I do in doing this? In doing this, I had to do no work because W1 was equal to 0. Okay, why? Because there was no field. Basically, it was free for me to just bring it from infinity to there. Now let me bring the second charge, that is Q2, to its appointed place. Suppose the appointed place is somewhere here. Okay, I do it there. So that will be my W2. So how much will be W2? W2 would be, so this distance between the charges, let that be R12. So I have brought Q2 in presence of the voltage due to the potential due to Q1. So this is Q1 by 4 pi epsilon naught R12 to the place where I have brought. Now let me do the third one. Let's take the third one and put it in this, let's say the appointed place is, let's say here. Okay, and I fix it there, and then the distance between Q1 and Q3 is R13, and between Q2 and Q3 is of course R23, and so I can write down the W3, that is the third stage, as Q3 brought it into the potential due to Q1 and Q2. So this will be Q1 by 4 pi epsilon naught R13 plus in the potential at the position of Q3 because of Q2. So that would be R23. Okay. So now what is in doing all these three steps, what is it, how much total that I have really done? I can now sum it up. W1 was 0, that is W2 plus W3, and that I can easily do. So 1 by 4 pi epsilon is common, so I can take it out, and this is Q1 Q2 by R12 plus Q1 Q3 by R13 plus Q2 Q3 by R23. I've just written down all the terms. Now suppose I keep doing this for n charges. Okay, so what would I get? It is quite easy to now generalize and write it down. Okay, so that will be 1 by 4 pi epsilon naught. I am assembling step by step, and hence I put a condition that I should be less than j if I'm writing for the ith step, and sum it all up, the qi qj by rij. Now this particular, so I've written it down here also. All right, so now what does this particular condition really mean? That I don't I just want to ensure that the sum over each pair is only once. Okay, so this condition is really to ensure ensuring that each pair is counted once. But that's an odd. Okay, so is there a first thing, note that it doesn't matter in which order I assemble. If the configuration is fixed and if the charges are being brought to their places, then whether I first bring Q3, then Q1 or Q2, in the order doesn't matter. Okay, and so this is a very artificial and odd condition to put. So since the order doesn't matter, how I bring it there doesn't matter. What I can do is I let double counting be there, but since I exactly know that I'm double counting, I can put in a correction factor of half, and hence instead of this I can write down that my total W is half. I'm introducing, and I'll allow double counting, okay, for each pair twice, and hence I'll put this value half 1 by 4 pi epsilon naught, and I would, okay, so then only thing that I need to make sure that this is due to I is not equal to j not equal to I sum it over qi qj by rij. So I have relaxed this condition of I being less than j, so I allow double counting, but I make sure that I just make it half. I don't lose, and this is a lot more neater. All right, so in that sense, this is for my n charges to be assembled, that's my work done. All right. Now this is quite, there is a prettier way to write this down, write down this summation, because you will realize that the what the potential at the position of the ith charge is nothing but, if I'm looking at the ith charge, is nothing but 1 by 4 pi epsilon naught sum over the potential due to all other charges. So I have to just make sure that J is not equal to I, because I am looking at the ith charge, and this is Qj by Rij. So the potential at V is equal to V at Ri, the ith position where I am putting the Qi, this is the potential due to all of the charges. Hence, it is now much even easier to write down. My W is half. Now all my n charges I can bring it down 1 to n, and so Qi for each charge and the potential due to all other charges V R J. Now that's so all the summing up that I was trying to do for you, just to show that I just need that half factor. Okay, so this double counting, and hence this half factor here I picked up by I let. Okay, yes. Now this is for a discrete charge, but this is easily generalizable to any discrete to any continuous charge also. So that for continuous charge, what will it be? It will be W. Let me write down W. That half factor. So I'm just making that the integral of V dq. That's the energy stored in the charge distribution. Of course, I can have different kind of charge distribution. If it is the volume charge distribution, then this will become W is equal to, for volume charge distribution, this will say that half V rho d tau. R I'm not writing down. For surface charge distribution, this will take the form of V sigma dA. I'm just expanding dq. Okay, and for line charge distribution, this will become W is equal to half V lambda dl. Now, what is the integration over? Okay, the integration is the integration over the portion which includes all charges. Integration over all charges in the configuration, the volume, line, or the surface in which all the charges are, all charges in the configuration. Okay, and I'm hoping that configuration, it's a localized charge distribution in the configuration. Okay, so we can take the sort of the master formula in this case is the is half V dq is the, okay, but V of R and rho of R d tau. That is indeed the master formula for charge configuration, finding out the work done and hence the energy stored in the. One thing you can notice that when I was actually bringing in charges and collecting the work done, this could have been positive or negative, okay, depending on, okay. So if what does a negative work done means? Meaning it was getting attracted, okay. So this particular formula would allow for both positive and negative, and that can be curious. I'll comment on that, okay. But it is simple to do. You can integrate over even a much larger space, okay. You can integrate over much larger space because you know rho is 0 there, okay. That where is included. You can integrate over any space, any volume, as long as it includes all the charges that you want to. It includes all the charges, because in rho is 0, so it doesn't contribute to the energy. So integration could be over the volume in which is larger than even where the charges are stored. Now, so that's I'll comment on that formula, but that's the we can now convert whether we can obtain in terms of field. Okay, so I can always write down the W in terms of field because I know rho. Okay, I know from what is rho. Rho we already know that it is epsilon naught divergence of E. Hence, I can change the above formula as epsilon by 2 divergence of E V d tau. So I've replaced basically the rho by this. Now you can see that in this case there is a differential here and there is a scalar here, and that immediately reminds us that I can do integration by parts and transfer this differential to V. What is the motive? If I can transfer this, so the appropriate differential to be transferred to V would be the gradient. And you can see if I transfer that, then that will be gradient of V, and E, gradient of V will give me E. Okay, so there is incentive to do integration by parts. Okay, so let's integrate by parts, and if you remember, it's an easy formula to remember for a parts integration. Integration by parts such that we transfer the differential, and so that will become, of course, epsilon naught by 2. So we pick up a minus sign in transferring. Then you remember my earlier lecture in which I was, so now this appropriate differential is of course gradient d tau. Okay, so we pay in terms of a minus, and the calculation of the function at the edge border. For the volume, the border is surface, and so this is over the surface, both V, E dot d A. So this is our appropriate volume of this appropriate surface. Okay, so this is simply by integration by parts. Okay, that is, I picked up a minus sign, transferred the differential and the function to be calculated at its border. Okay, so that is now even more attractive because this minus and grad V is minus and grad V is nothing but E. So the first term becomes epsilon naught by 2. Okay, so over the appropriate volume E square d tau, E dot E, E square d tau. And of course, then wherever the volume is enclosed by S, that V, a potential there, and the field there, dot dA. That's the energy stored. Okay. Now you can imagine that this quantity E would be, roughly speaking, let's roughly speaking, E goes as 1 by R square, VA goes as 1 by R, and a surface integral like that would go as R square. So roughly this quantity, okay, this is a rough argument of, okay, this is goes as 1 by R, roughly speaking, this quantity. Okay, and if we imagine this, of course, you can include, okay, encloses the charge, whatever volume, should enclose charge, okay, but otherwise whatever volume can be anything, this volume. Now the first thing I can do is I know that all this V should be going to infinity and so on and so forth, so I can let this surface go as this volume can be as big as possible. If as possible, then this term goes by 1 by R, and for very large volume this will simply vanish. Okay, and hence if I consider it to be all space, okay, so if my volume is all space, then this reduces down to, okay, the first term alone is square d tau, because the surface term then does not, okay, this is all space. Okay, now that's an important finding, okay, that if I know my E, then the field, even if it is E square all space, then I can obtain. So in some sense, we have gotten, this is the third formula for our, this is the third formula. This is our, any of this should be valid for our energy calculation. dq, so I'll call this as VDQ method. This is both surface and volume and surface, and this is of course only the field. So that's looks quite neat, but there are certain aspects that need to be pointed out. First thing is the VDQ formula, we said, can be positive or negative. Okay, can be positive or negative, because depending on what kind of V and what kind of sign, positive or negative. Now what does that energy negative means? Of course there is attraction, I don't have to do work, but you can see that this third formula is always positive. Okay, so but E square, okay, this is E by E square d tau, okay, is always positive. Now, so that seems to be some inconsistency. Well, they are inconsistent, though it looked like a very tight fit derivation, but there are some inconsistencies that we cannot overlook. Okay, there are energy. When you talk about energy, then there are two parts to it. Okay, so total energy can be, so at different contexts one could be talking about different things. That is self energy, that is of actually producing the charge distribution. self energy plus the interaction energy. Okay, so for example, when we were doing the VDQ method, okay, we were not creating any charge. Okay, the charges were easily already available, and in fact, the energy required to create a point charge will be almost like infinity. So VDQ method was only highlighting probably the interaction energy while assembling it. Okay, but this method is actually field. Uh, this tells us the field. So, well, we know. So it can be. This has to be positive definite because this is stored in the. This is stored in the field itself. But interaction energy is a relative term to self energy. Okay, and hence that can be positive and negative. So the two look similar, but they are actually answering in some ways different questions. Now the next question is, where is this? Where is it stored? Where is the energy stored? Well, is it stored in the field or is it stored in the charge distribution? If it is, as if it looks like, if suppose this is the charge distribution, in which, okay, so is the energy, when I'm integrating over this, it looks like if the energy is stored here, or is it everywhere in space? In the space. So where is it located? Well, in some sense, that's not the right question or the meaningful question. All we have is a way of, okay, computing it. Okay, way of computing energy. Now, you cannot talk about in a field theory like this, where is it stored? Okay, so it is not stored in any particular, you are just calculating how much work was done and how much work it can possibly deliver if you disassemble it. Okay, so it is configurational. Okay, so you cannot say that whether it is located within the charge or in the field, or it's not a question that is a very well posed question. All right, the most important part to a distinction is we saw that E follows superposition, V, okay, obey superposition principles. Superposition. Does energy also, total electrostatic energy superposition? Obviously not. Okay, so energy does not obey superposition. Why? Because it's not linear, it is E square. Okay, does not obey superposition. Because we know, for example, the total energy that we are saying is epsilon by 2. Okay, I can write down this as E dot E, d tau E square. Okay, now suppose E is E1, it is a superposition of E1 plus E2. Okay, then what does this become? Epsilon 2, this will be E1 and E1, of course. Okay, so E1 square d tau would one be termed. There would be a term which would be E2 square d tau, but there will also be a term which is epsilon 2. Okay, there will also be a term which is E1 dot E2 tau. So there is a interaction term, which these are the self terms, but these are the interaction terms. So superposition is not obeyed by energy because interaction, because of course is non-linear, is E square. So having made those comments, Let me now take up some example. Okay, let's take up the example of let's call me example 2C as 1. Okay, so this is the energy, let's say a shell. We take up a shell, okay, electrostatic energy of uniformly, so this I'm taking a very simple case, uniformly charged spherical cell. In fact, you can do this in many different ways, okay, and all should give you the same of radius r, let's say of radius r, and sigma is the charge density. Or let's, instead of charge density, let its total charge, let's say total charge Q, uniformly. Since I already said uniform, so let's in terms of, write it down in terms of radius r and the total charge Q. Okay, so let me do one first method. We'll use method 1, okay, which I call as the VDQ method. Okay, I'll refer to it as VDQ, that is in the charge assembly method. Okay, so then W is of course half V. In this case, dq is sigma dA. All right, and what is V at R is equal to R? It's the total charge is all at the shell level. So this is of course 1 by 4 pi epsilon naught. Total charge is Q by R. It is easy to write down that way, and hence I can write down this as half 1 by 4 pi epsilon naught. Take out, then Q also I can take out because it's a constant. R I can take out, so all that remains is sigma dA, and that is nothing but Q. So it becomes 1 by 8 pi epsilon naught Q square by R. Simple, right? This is the energy stored in the charge assembly by the VDQ method. Now let's take the field method. Method 2. In principle, I could use all the 3 different formula. Okay. So first, to figure out what is E in this case, for a spherical cell, it is a no-brainer. Okay, so that is 0 is of course inside. So for that, I should know the field everywhere. And what is outside? Outside is as if all the charge is centered at the origin. So this is Q R square is of course R greater than R. This is R less than R. Okay, so in that case, what is my E square? E square is Q square by 4 pi epsilon naught square R to the power 4. Correct. So W total, so let's find out W total is over all space. We are going to do the integral. So of course I'll take out 4 pi epsilon naught square out, and then integral of q square by r to the power 4 r square sine theta dr d theta d phi over all space. Correct? So this is 0 from 0. So this is r to infinity. Okay? Over fully. So this is traditional integral. We can always, so 1 by 2, 8, 16, 32 pi square epsilon naught, 16 to 2, then q square from the phi, and this integration will give 2, 4 pi, and then of course r to infinity integration, I'll get only 1 by r square from there and dr. Alright, so that is simple. So that again gives me 1 by 8 pi epsilon naught q square by r. Is that the same as what we obtained here? Absolutely. So this problem of the difference between the two methods do not come in case of continuous charges, because creating continuous charges, differential charges, is of course doesn't cost energy at that time. So the same answer, you could use even the partially some volume and the third method and some surface, and will come to the same conclusion. But the methods are not always applicable. All these methods are not always applicable. For example, take as a home task. Okay, suppose I want to find out the energy stored in a charge configuration, which is a disk of a radius r and sigma. Okay, this is sigma. Now, can you use the field method here? It's very difficult to write down the field everywhere in space. Can you use E method here? E here for calculating all energy, but it should be very possible to do. Okay, the chart. So different formula can be, one of them can be preferred in any particular situation. So there will be some problems in the home assignment, especially the solid sphere. I have done a shell, but solid sphere can be solved in 4 different ways, and I will urge you to do in all 4 ways. There are rare problems which can be done by all methods. Okay, so in fact, some of those methods I would like you to work out so that you could choose a proper method when it comes to another problem in which a particular method would be preferred. Thank you.